அப்ப நம்ம அடுத்த பகுதிக்கு போலாம்.
Welcome to our lecture line. Another great kind of lost it here. Try this again. Welcome to our lecture line. Another helpful tool is being able to add sinusoidal functions that have different amplitudes, have the same. I need more coffee. All right. So yeah, got what C is equal to times the. Let me start over. Let's start to our lecture line. Another great tool to have at your disposal is knowing how to add sinusoidal functions, especially when their amplitudes are not the same. When A and B is not equal, how do you add these together? Well, it turns out that's going to be equal to C times the cosine of omega t minus the phase angle. Now the question is, what is C equal to, and what is that phase angle equal to? Well, first of all, C can be found by taking the square root of the sum of the squares of the amplitude function, a squared plus squared. And secondly, to find the phase angle, that will be equal to the arctangent of the ratio of B over A. Of course, we do have to take into account the signs of B and A, if they're positive or negative. So as an example, if it's nothing like a good example to show you how to apply that, let's go ahead and add these two functions together. Notice that A and B are not the same. In this case, note that that's going to be equal to C times the cosine of omega t minus the phase angle. First, we need to find C. C is going to be equal to the square root of A squared plus B squared. So A is 2 and B is the negative 3. Squaring it, sign doesn't matter. This will be equal to 4 plus 9 equal to the square root of 13. And of course, if you want a decimal number for that, square root of 13 would be 3.6. 3.6. This would be equal to 3.6 times the cosine of omega t. Now the phase angle. So the phase angle can be found by saying B is equal to the inverse tangent of B over A. Now in our case, B is a negative 3 and A is a positive 2. Take 1.5, make that negative, take the inverse tangent of that, and we get a minus 56.3 degrees. That's equal to minus 56.3 degrees. And of course, since we're subtracting the phase angle, this becomes plus 56.3 degrees. And here that would be the answer of our simple example. Again, tend to have at your disposal when you need to add sinusoidal functions that have a different amplitude. That's how it's done.
அப்ப என்ன பண்றோம் அப்படின்னாக்க, மிக முக்கியமாக இந்த ஏசி ஃபண்டமெண்டல்ஸ்ல நம்ம என்ன பார்க்கறோம்னாக்க, சைன் ஏ காஸ் ஏ இந்த இரண்டினுடைய ட்ரிகோனோமெட்ரிக்கல் ஐடென்டிட்டிஸும் இந்த ஃபார்முலாஸும் ஞாபகம் வச்சுக்கிறோம். இப்ப அடுத்தது போலாம்.
Welcome to our lecture line. Here we're going to introduce ourselves to the concept of phasors. Now, before we actually show you the phasor diagrams, we're going to try and do a graphical representation of the sine and the cosine function, sinusoids, to see how this kind of relates to one another. Now, notice if we first draw out the cosine and sine function of a varying voltage source, for example, here we have cosine function, which is B max times the cosine of omega. Here we have the sine function, E of t is equal to B max times the sine of omega. Now notice there's a phase difference between the two. When time is equal to 0, the cosine function has its maximum value and the sine function is equal to 0. After we go 1/4 of a complete cycle, when we're over here, that would be a shift in omega t of the value of, so this value right here, let's say this is pi over 2. So when we do a complete cycle, when we go from here, here, back to here, this here would be 2 pi. So 1/4 the distance on the omega t axis. See that at this point, sine function has its maximum value and the cosine is equal to 0. If we're going to graphically represent that, we're going to put that on a graph like this. Notice that the positive x direction, the horizontal axis, the x direction, we call that the positive value at equals 0. See that cosine function is pointing to the right because at equals 0, the cosine function has maximum positive value. But at that point, the sine function is equal to 0, and it's going to require another 90 degrees in omega t, or another pi over 2 for sine to reach its positive maximum value. So if you assume that graph is going to oscillate or rotate around this point right here, notice it's going to take a 1/4 of a cycle, or 90 degrees, for a cosine to go to here, which means has 0 value in the positive x direction. That means cosine function will be 0, and the sine function will now have rotated out here, and it will now have its maximum value after 90 degrees have gone by, or in other words, when omega t has increased by 90 or pi over 2, then have the sine as being its maximum value. So you can see that the sine function lags the cosine function by 90 degrees. That's what we say. Sine function lags cosine function by 90 degrees. Now, when we take that concept, let's go back what we did on the previous video. We're going to add these functions together. 2 times the cosine of omega t minus 3 times the sine of omega t. Well, first of all, let's represent 2 times the cosine of omega t. If the cosine of omega t is equal to this function right here, then twice that will be twice as long. So it's kind of like a vector. Let's go ahead and draw that here. Here, call this 1, call this 2. This here represents 2 times the cosine of omega t. Now we want minus 3 times sine of omega t. Well, plus 3 times the sine of omega t, and let's purple right here. So we go like this. And I call this a 1, I call this 2, I call this 3. So 1, 2, and 3. Notice this is in the positive direction for the sine, the positive sine of omega t, 90 degrees behind the positive of the cosine of omega t. And notice this is plus. This is plus 3 times the sine of omega t, and it's pointing in the downward direction. So if I want to minus 3 times the sine of omega t, and then have to add 180 degrees, I have to turn it upside down basically, and have to go in this direction. This here would represent the minus 3 times the sine of omega t. 1, 3, like that. Or actually minus 1, minus 2, and minus 3, that way to label it. Now I'm going to add the plus 2 times cosine of omega t. So minus 3 times the sine of omega t, and it's basically a vectorial addition. So I'm going to do that. Let's use the vectorial or parallelogram method, like this. And notice, let me purple color. This here would now be the sum of those 2. This would be equal to 2 times the cosine of omega t minus 3 times the sine of omega t. And if I want to know the phase angle relative to the positive x-axis direction, so the positive value for the cosine function when time is equal to 0, and now I'm looking for the phase angle, let's call it phase angle B. And I can see that the phase angle right here would be equal to inverse tangent of, well, let's see here, that would be equal to the positive value right here, that would be the value of 3 divided by a value of 2. Now here you say, well, wait a minute, isn't the equation as follows? Isn't the phase angle equal to inverse tangent of b over a, and b would be the minus 3 value, and a would be the positive 2 value? The answer is no, that's correct. So we would get b is equal to the inverse tangent of b, which would be a minus 3, over a, which would be a 2. If we then calculate that, we get a negative angle. So we go ahead and we get 3 divided by 2, that's negative, and take the inverse tangent of that, we get minus 56.3 degrees, minus 56.3 degrees. But remember that the addition was going to be equal to square root of a squared plus b squared times the cosine of omega minus the phase angle. So the minus the phase angle, we have minus times minus becomes plus, we get a positive phase angle. That's what we get over here. This is equal to a positive 56.3 degrees, which is what we graphically see here. here you can see that if you simply take a look at the graph, I'm going to add these together. This is a positive 56.3 degrees, which is now the sum of function phase angle produced by that sum. So this is what we mean by a graphical representation. Result, when we subtract this from that, you get a result here that has an amplitude of about, I think it was about 3.6 if I remember right, and that phase angle 56.3 degrees ahead of the cosine function, since we're subtracting the sine function, which normally points downward. That's our initial introduction to graphical representation of sinusoids, which will lead us.
அப்போ மெதுவா என்ன பண்ணிருக்கோம்னாக்க சைன் வேவ்னுடைய ப்ராப்பர்ட்டிஸை சொல்லி அந்த சைன் வேவ் வந்து ஏசி சிக்னலோட கோயின்சைட் ஆகிறத சொல்லி ஃபேசர் அப்படின்ற ஒரு வார்த்தையை இன்ட்ரடியூஸ் பண்ணியிருக்கோம். ஆனா இப்ப ஃபேஸ் ஆங்கிளை பத்தி தான் பேசிட்டு இருக்கோம். ஃபேஸ் ஆங்கிளை பத்தி பேசி ரெண்டு ஃபேஸ் ஆங்கிளை கம்பேர் பண்ணி அவைகளுக்கு இடையே இருக்கக்கூடிய ஃபேஸ் டிஃபரண்ட்டையும் ரிசல்டன்ட் ஆம்ப்ளிடியூடையும் பார்க்கக்கூடிய ஈக்குவேஷனை பார்த்தோம். பிறகு
Welcome to our lecture online. Here again, hoping to get a better understanding what phasors are. Let's go ahead and again represent a sinusoidal function by its graphical representation. Realize from the last video that positive cosine right on the positive horizontal axis and the positive sine function in the downward direction on the vertical axis. A positive phase angle is from the horizontal axis, vertical axis, and a negative phase angle on the horizontal axis, negative vertical axis. So here we have a general format of the equation where the voltage as a function of time is equal to maximum voltage times the cosine of omega plus the phase angle. And in this example, we're going to let it equal 5 times the cosine of 40 plus 20 degrees. So from this, you'll be able to interpret the amplitude, the phase angle, the angular frequency period, and you'll be able to draw that function on our graph right here. So first of all, the amplitude. Well, the amplitude is the number from the function right here. So 5 volts, and yes, units are volts. The phase angle here is going to be a plus 20 degrees. So 20 degrees, units there is degrees of D. The angular frequency, well, the unit there would be radians per second, and it's the number from T, omega. So that's equal to omega, which is equal to 40 radians per second. That would be units for angular frequency, radians per second. Now the frequency. Well, it turns out that the angular frequency, omega, is equal to 2 pi times the frequency. Therefore, the frequency is equal to omega divided by 2 pi. Go ahead and plug that in here. Omega divided by 2 pi. Then have 40, that's equal to 40 radians per second divided by 2 pi. That would be 20 divided by pi, and units now become cycles per second. So the 20 divided by pi equals 6.37 cycles per second. But cycle would be one complete cycle on the oscillatory function. And then finally the period, which is defined as 1 over frequency. In this case, P, that would equal to 1 divided by 6.7 cycles per second. Cycles per second. So if I spelled that right here, cycles per second. So if we take the inverse of that, that would be equal to 0.157 seconds. That would be the period. So one complete cycle in this particular example would take a little bit more than 0.15 seconds. Now let's go ahead and grab that on our graph right here. First of all, the amplitude is 5. So that would be, this is the 5 away from the point right there. So we can draw a circle and let the radius of the circle represent, so the radius of the circle represents the amplitude. In this case, that would be 5 volts. Next, the phase angle, positive 20 degrees that would be from the horizontal positive axis 20 degrees up. This is equal to the phase angle of 20 degrees. Then you can see that we can actually draw this. Looking for my red pen. There we go. If we're going to draw that, it would be represented by this. So the length of this vector here, that's equal to 5 volts. The direction is 20 degrees above the cosine of omega function, and that will then properly represent phase angle and the amplitude. What about the omega? What does that mean? That means in a time of 0.157 seconds, this vector will rotate all the way around and get to the exact same position as before. So the time elapsed to make one complete cycle will be equal to 0.157 seconds. And if we take any portion of that time, you see the vector will be in different places. That's what we mean by a sinusoidal voltage, that amplitude will continue to change, will go from 0 to max, 0 to negative max, and so forth. See that at this particular snapshot, time is equal to 0. This is the current location on the graph of this particular function. And equal to 0, 5 times the cosine of 20 degrees. That's how you would then represent it. If you now add 2 pi to that, then you would again come back in the exact same position with everything. So then you would plus 2 pi, the repeating sinusoidal function, exact same location when omega pi greater than this case. That's the graph.
அப்போ ஏசியினுடைய ஃபண்டமெண்டல்ல பவர் பாயிண்ட்ல விளக்கிட்டு அந்த ஏசியினுடைய ஃபண்டமெண்டல ஒரு சினுசாய்டல் வேவ் ஈக்குவேஷன்ல இருந்து எப்படி கண்டுபிடிக்கிறதுன்றத பார்த்தோம். இப்போ அடுத்த பகுதிக்கு போறதுக்கு முன்னாடி ஒண்ணு நல்லா புரிஞ்சுக்கலாம். டிசி கரண்ட் அப்படின்றது பாசிவ் எலிமெண்ட்ல எப்படி வேலை செய்யும், ஏசி எலிமெண்ட்ல எப்படி வேலை செய்யும், அந்த ஏசி எலிமெண்ட்ல இருந்து வெளியில வரக்கூடிய டைம் கான்ஸ்டன்ட் ரிசனன்ஸ் அப்படின்ற 2 ஃபங்க்ஷனுக்காக இந்த சாப்டர் படிச்சுட்டு இருக்கோம். இப்ப அடுத்த பகுதி டிசில பாசிவ் எலிமெண்ட்டுடைய பிஹேவியர், அடுத்து ஏசில பிஹேவியர் கம்பேர் பண்ண இந்த சாப்டர் முடிஞ்சு போச்சு. சரிதானே? மீண்டும் சந்திக்கலாம்.